Okay. So now module 4. So in the module 4 we are going to do fault analysis. Okay. So you have already completed some part of fault analysis during protection, right? You know that how many types of faults are there? We generally categorize faults to be two types. No. Shunt faults, series faults. Okay. Shunt faults will be of two types. One is symmetrical faults, one is unsymmetrical faults. Okay. But when we do fault analysis in power systems, we are going to use only symmetrical faults. Why? When we do fault studies, we generally go for symmetrical faults, not unsymmetrical faults. Though unsymmetrical faults are the most common. Okay. Severity. Okay. We need to design the power system so that it can withstand the highest, what is the highest possible fault level, so that we can decide circuit breakers. Okay. So symmetrical faults are generally used for fault studies. Okay. So in this module, okay, so triple line to ground, or we can say certain short circuit or alternators. Okay. So these three classes we will devote towards symmetrical faults or short circuit analysis. Okay. Next three classes we will discuss unsymmetrical faults. Okay. We are not going to do advanced analysis. Rather, we will discuss symmetrical components, sequence networks, and then how to compute unsymmetrical fault current. Okay. Okay. Three classes will be devoted to symmetrical faults. So first class we will discuss what are the various types of transients in the power systems. So when I say transients, it also includes switching transients, lightning transients, and also faults. Okay. So the power system must be designed so as to withstand all kinds of faults. Correct? So, power system may be considered in the following three states: operated in static equilibrium, when the system models turned out to be non-linear algebraic equations. But this is load flow. Okay, the first case is load flow. Okay, in equilibrium, we take a snapshot of the system. Okay, so there we get a set of non-linear algebraic equations known as the load flow equations. Second one is small scale dynamic perturbations, okay, which can be modeled in the linear differential equation, and this is known as small signal stability. We have already studied about small signal stability. Okay. And finally, this module we are going to discuss the nature of the major disturbances. What happens when major disturbances occur? We have already seen in terms of equilibrium criteria and swing equation. Right? But what is the nature of this major transient, that we will see in this first three classes. So these are collectively known as transient. Okay? So you can write down, mention there, major disturbances in the power systems are known as transients. If you go for higher studies, at PG level you can have a separate complete paper on power system transients. Okay, the nature of the transients. So, major disturbances in power systems are collectively referred to as transients. Okay. So, how many types of transients we have? We will consider three types of transients. One is ultra fast transients. Okay. three kinds of transients we consider. One is ultra fast, which are very fast. These are known as surge phenomena. Okay. This type of transient is caused by atmospheric discharges on the exposed transmission line and by the abrupt and but normal network changes known as switching operation. So you can have two kinds of such ultra fast transients known as lightning and switching. Switching because of human made switching operations and lightning because of the atmospheric phenomena. And one such event you are going to see in the cycle 2 of power system lab 2, where you will see impulse generation. You have seen two parts in high voltage lab. Okay, the third part will be impulse generation. Okay, that will be in cycle 2, where there you will see how these ultra fast transients are simulated in the laboratory. Okay. So what happens during this switching operations? This cause an electromagnetic wave traveling at the speed of light, giving rise to reflected wave and hence surge voltages. Okay. So you have read about reflected wave, transmitted waves in your EPTD paper. Okay, or power generation, transmission, distribution. So what happens is when a lightning wave or a switching wave travels in the power system, it results in a reflected wave, and when they are combined, it results in very high value of voltage in the power system, which may result in failure of the insulators. If insulation failure occurs, then there is a short circuit. Okay, that is the purpose here. If the insulation is damaged, the result is short circuit. That is the whole purpose. Okay, so what is the first kind of transient? Ultra fast transients known as lightning or switching surges. Okay. The second kind of transients are medium fast transients. Okay. These are system transients caused by abrupt, abnormal structural changes. Okay. So these are basically the faults that we generally analyze to compute the fault current and design various reactors, okay, or some arrangement in the power systems. Okay, circuit breaker reactor ratings are decided based on this. Okay, so the second kind is short circuit, which are also known as medium fast transients. I started with A, so this is B. This is B. B is short circuit or medium fast transients, and C is slow transient. Then you will see. So what is a short circuit or a medium fast transient? This can be, as we discussed at the beginning of the class. So there can be shunt faults or series faults. In shunt faults, we have two types. One is symmetrical faults, which is known as triple line to ground. Okay, and the other kind of faults can be of double line to ground, and line to line. So as we know, majority of the faults are line to ground faults, single line to ground faults. Okay. But for fault studies, when we decide the rating of the reactors and circuit breakers, we generally use this one, triple line to ground fault, because that is the maximum fault current that the system should be able to withstand. Okay, circuit breakers and reactors. Okay, but for switching and lightning surges, we have different kinds of devices known as surge arresters. Okay, ultra fast transients, we have surge arresters. Right? Okay. The first three are known as shunt faults, whereas the third is a series fault. Okay, it's line to line faults. Actually, this is not exactly a series fault. Another kind of series fault is breaking of conductors. Okay, if a conductor is broken in between, then that is also a fault that is known as a series fault. The third type of transients is a slow transient. Okay, so slow transients are the ones we discussed during our stability module 3, which are oscillations because of a fault in the machine. Okay, these are not very fast because of the rotating nature or the nature of the inertia. We have a moment of inertia down there. So because of the huge mass, this is not that fast. Okay, so these are known as slow transients. Okay, hunting phenomenon. So this is a slow transient, but nevertheless it is a transient. A short circuit is always accompanied by instantaneous collapse of bus voltages and reduction power. Why instantaneous collapse of bus voltages? Because it's a short circuit. Okay, if it is a short circuit, that means voltage will be zero. Due to constancy in power input, electromechanical transients may result which may pull some or all machines out of synchronism. Okay. So that means though power generation is occurring to meet certain kind of load, but still it is going to the ground because of the short circuit, which means that there is no load, but power is being generated. So it will simply result in increase in the rotational speed of the machine, which are known as electromechanical transients or the slow transients, because those are heavy machines and hence these are known as slow transients. Okay. So also known as rotor swings. Okay. Next. Now what exactly happens when there is a transient on a transmission line? So a transmission line can be considered to be a RL circuit. So draw this RL circuit. Draw this circuit. A transmission line can be considered to be a RL circuit, okay, where a sinusoidal voltage of Vm sin omega t plus alpha, Vm is root times V, so Vm sin omega t plus alpha is applied and a short circuit is assumed to take place at t equals to 0. Okay. What is alpha? The parameter alpha, or the phase angle of the wave, controls the instant on the voltage wave when the short circuit occurs, and therefore the amount of the current. Okay. If the short circuit is occurring at the zero crossing, that means the current is less. So you might have read in your circuit breaker theory that we always try to do that circuit breaker opening during zero crossing, so that we have less voltage surge. Okay. Under this short circuit, did you draw the circuit? Under this short circuit, the current is given by the peak value of the current divided by the impedance of the circuit with a phase angle theta. Okay. Omega t plus alpha, sin omega t plus alpha is the nature of the voltage wave. Okay. So voltage divided by impedance is the short circuit current. Now this impedance is the magnitude, as you know, r square omega l square whatever, and phase angle theta. Okay. And this current has two parts. One is known as the steady state component, one is known as the transient component. Okay. Steady state component is given by this voltage by impedance, whereas the transient component from circuit theory is given by this equation. Okay. And this is known as the symmetrical short circuit current, okay, which reduces over time, okay, as the time passes. So write down the expression for both the currents, steady state current and the symmetrical short circuit current. Okay. So this is symmetrical short circuit current, which is a constant current, symmetrical, whereas there is a DC offset current which is superimposed on this. Okay, DC offset current which is superimposed on this. We'll see the nature in the next slide. Write the expression. Done? So this is the nature of the current when there is a short circuit on a transmission line. So when there is a short circuit on the transmission line, this is the nature of the current. So the first one is a symmetrical current on which is superimposed a DC offset. Okay. Because of the combination of both, we have a waveform like this, which is reducing, which is passing in this form because of the DC offset. Okay. And this follows from the circuit theory. Okay. This follows from the nature of the circuit, because we are considering the transmission line to be a RL circuit. Okay. Done. So this is first part is what happens or what is the nature of short circuit when it happens on a transmission line. Next we will see for the generator. So I hope all of you have completed the short circuit experiment. Sudden short circuit on the alternator. Okay. Okay. So the next part is short circuit on the synchronous machine. Okay. So there you have seen that the waveform is something like this. Okay. Short circuit current waveform is that you see in the digital storage oscilloscope. Why you use storage oscilloscope? Why not normal oscilloscope?
Small time.
Yes, it's very fast. We cannot capture in an oscilloscope, so we need a storage oscilloscope. Okay. And the current waveform that you see, okay, the first part is known as the subtransient period. So here the current is very high. The first cycle is taken as the subtransient current. And after say 3-4 cycles, we take the period as the transient period. Whereas the final current is known as the steady state current. Now based on this, what you can infer? You can infer that initially the impedance of the alternator is very high, very low, because current is very high. Initially the short circuit current is very high. That means, so what you see here? You see that, so I will say ID double dash, which is short circuit current during subtransient period, greater than the short circuit current during transient period, greater than the steady state current ID. We use D because of direct access concept. Okay. Okay. So it simply means that the direct access subtransient reactance is the lowest. Okay. Now what is this reactance? This is the machine reactance. Synchronous machine is simply a winding. Synchronous machine is simply a winding. This is the winding reactance, which you can also get from your machine's knowledge. You know that you can get the value of XD or XS. It is also known as XS, synchronous reactance. XD because of this, that is another component XQ for silent machines. Okay. So XD or XS, so that you get from ACC or OCC. So for a machine, suppose the machine that you have done sudden short circuit and you have got some XD value from this curve, okay, that should exactly match with what you operate using ACC and OCC, because that is the steady state reactance value or the actual reactance of the machine. Okay. Now the question is, since it is a simple winding, a single winding, how can it offer three different reactances? Right? It's the same winding, isn't it? We are not changing the winding of the alternator. So how is it possible that it is offering three different reactances on at different times? During the fault, subtransient, after some time still higher reactance, and after some time highest reactance or the original reactance. Why it is offering like that? Who can tell? It should be same, isn't it? It's the same machine. It's the same machine. Right? I told you once, it is exactly similar to how humans behave. Right? When we are in a very good mood or emotionally very stable, then we don't react to situations. But suppose we are hungry or we are angry and tired because of something, then our reactance is or resistance is very low. We get angry too often. Okay. It's the same person who is behaving differently under different situations. Same is applicable for alternators. So it behaves differently or the reactance changes depending on the time or during the fault. Okay. So why exactly it happens? Because this is the theory that has been put forward to explain the behavior. Why alternator is providing the lowest reactance in the initial fault period and further. Actually, that is a continuous process. The reactance is slowly increasing, but we have decided to just make it categorized into 3 types only: subtransient, transient, and steady state. Okay. So during normal, from your machine's knowledge, you know that during normal operation, the machine reactance is basically the armature reactance plus the leakage reactance. Okay, that is during normal operation, and that is known as the synchronous reactance HT. However, initially during the fault, the damper winding reactance, the field reactance, and the armature reactance, they come in parallel. Somehow they come in parallel. Okay. So that means field winding reactance and damper winding reactance, which are completely separate entities, they suddenly come into picture during initial period of the fault. And because of this parallel combination, as you know, when reactances are in parallel, the effective value is less than each. Okay. So this is the lowest value. Similarly, during transient period, the damper winding reactance is no more in picture. The field winding reactance and the armature winding reactance, they come in parallel. Okay. If you are appearing for interviews for companies like DHL, they might ask you this question, because companies which build alternators, they do short circuit tests. Okay. Certain short circuit tests to give these parameters, numerically obtain or practically obtain these parameter values for huge MBA level generators. They do that. Okay, they have a separate arrangement. Okay. Okay. So now, again explaining the same thing mathematically. Suppose Xt is the direct axis synchronous reactance, Xt dash this I have to draw. This is transient reactance. Direct axis, transient reactance. Ht dash. Ht double dash is direct axis subtransient reactance. Then during transient period, we have this situation, and during subtransient period, we have this situation. Write down this. And therefore, the reactance during subtransient period is the lowest, and resulting in the highest value of current. Now, circuit breakers must be designed that they handle or they can handle this highest value of current. Okay. When a sudden short circuit is applied to a synchronous machine initially operating under open circuit conditions, then the subtransient current is given by this, which is the highest. After few cycles, it becomes the transient current, and finally it is steady state current. Okay. So these are known as steady state, transient, and subtransient components of the current respectively. Okay. So we discussed two things. One is what happens when there is a short circuit on a transmission line, and how the synchronous machine behaves when there is a short circuit on its terminals. Okay. Okay. So next. Next we will solve a problem based on these equations. Okay. Only these equations we are going to use and solve the problem. So we will solve question number 4.1.1. Solve this. You need to use only those three equations. Okay? Solve this. Okay. For this problem, for computing the short circuit current, we are going to use these equations. Okay. However, alongside these three reactances of the alternator, we are going to add the transformer reactance. Okay. And we will start with working with per unit values. In the problem, in the question, it is given Eg is 1 per unit. Okay. and these values are all given in per unit. So you are going to get all these currents in per unit. Then you calculate the base current. How to compute the base current? MVA rating divided by root 3 into voltage. Okay? Root 3 into line voltage, because we are using MVA rating, so it will be root 3 into line voltage. No need to convert into phase. So that is the base current on one side of the alternate side. Then you convert that to the high voltage side or transformer side. So that will be lower. On the high voltage side it will be lower. Okay? But we are asked the current on the generator side. Okay? You will see the answers here. So you see here. So subtransient current is simply 4.54 per unit. That means 4.5 times the rated current. Right? 4.54 per unit is 4.54 times the rated current. Similarly, here also it is 2.8 times the rated current. Note that the subtransient and transient as well as the steady state current, the current values are 90 degree lagging the voltage value, because it is, we are considering it to be a pure reactance. Okay? And here we are calculating the base current. We multiply the per unit current with the base current so as to obtain the actual value of the fault current on the high voltage side, on the low voltage side. Okay? And for others also we can do. Then next question is maximum DC component root 2 into I double dash, the subtransient current, which comes up to be 6.427 per unit. Maximum instantaneous current is maximum DC component plus this maximum subtransient current plus the DC component. Okay? And this one is the maximum value of the symmetrical AC current, root 3 times I double dash. Okay? So this completes, and this question you solve it yourself. So here for this question, second question, we are using a concept known as reactance diagram, where the generators are replaced by, write down, in reactance diagram, a generator is replaced by a voltage source with a reactance in series, which is the reactance of the alternator, maybe subtransient, transient or steady state depending on our requirement. Okay? So that is known as the reactance diagram. So for solving all these problems, we need to use reactance diagrams. Okay?